great honor to give a talk here, and I'm very honored because in the audience there are so many people who made fundamental contributions to the area. I want to talk about polylogarithms, cluster algebras, and Zagier conjecture. And this all is joint work with Alexander Goncharov. So basically, the whole talk has one idea which I want to pursue, and this is the only important thing in the talk. The idea is that cluster algebras, general cluster varieties, and cluster type structures are very much related to polylogarithms, and that they can be used to understand combinatorics behind functional equations for polylogarithms and so on. And all the concrete results I will state, they will actually be stated in the way to emphasize this idea and explain in some simple examples how it works. So here is the plan of the talk. So after some very brief introduction, I will talk in some detail about five-term relationship, which I guess a lot of people here know very well. But I will explain how it comes from the simplest cluster algebra type phenomena. Then I will talk about the logarithms and cluster algebras. This is the topic which was developed by Goncharov and was familiar before. And finally, I will very briefly talk about mixed state motifs and polylogarithms, and I will not come into too much details here. And in the end, I hope to finish with the relation between polylogarithms and cluster algebras, which is the main goal of the talk. So, for completeness, let me start with giving a definition of polylogarism. So it's, of course, very well known to a lot of people. So, classical. Polylogarism of weight n is the following function. So it's a function of one complex variable z given by the power series and this power series, of course, is converging only when the absolute value of z is less than 1, but it can be extended to a multivariate function on the whole projective line minus 3 points using iterated integral formula. I will also talk about single-valued version of this function. And let me just write down here the formula for the single version for completeness. So depending on evenness or oddness of the weight, is given by two different formulas. Okay, so this single-valued version has a bunch of nice properties which makes it simpler to study, the main of which is that it is a continuous function on the whole CP1, but it is real valued, and it is smooth, it is continuous but not smooth in 0, 1, and infinity. Okay, so in this introduction I just want to say why actually people study polylogarithms and
Log z to k.
Sorry?
Log z to the k.
Log absolute value of z
To the k.
to the
It's
k.
not quite absolute, but there should be a k somewhere.
1 second. Yes, absolutely. You're right. Of course.
Oh.
Of course, you're right. Yes, sorry. Okay. So.
Now, where is the power referring to?
Yes, I meant log power k of the absolute value of z. Okay.
And there is an index, is k also in the index of the polylogarithm?
Sorry, let me rewrite
N
it.
minus k.
So it is log power k of absolute value of z times polylogarithm with index n minus k of z. So there are two major reasons to study these functions, at least as I see it. So the first reason to study polylogarism is as follows. Everything? Okay. So polylogarism satisfies functional equations. So there are a lot of interesting functional equations for polylogarithms. And let me start with examples. So of course I'm not talking about the example in weight 1. Of course everybody knows the functional equation for usual logarithm. For n2, the functional equation was found by Abel, and I will give not the version for the classical version, but for the single value one, which is easier to write down. So here it is. This is a famous Abel five-term relationship for the logarithm. Okay. So there are a couple of proofs and interpretations of this equation, and I will talk about it a little bit later. But before that, let me say what happens in the higher weights. So for n equal to 3, the first functional equation, I guess, was found by Kummer, and a more general one was found by Goncharov, and there are some reasons to think why this equation is actually the more general one. Every other equation should follow from that, but it is not known. For n equal to 4, there were again some very simple and very degenerate equations found before by Kummer as well, but the first really serious one was found by Herbert Gangel quite recently, and I'm not completely sure, but I guess it has about 500 terms or something.
This one's not very recent, it's 25 years ago by now.
Oh, what's?
It was 4?
No.
No, he found one for n equals 7.
No. I mean not with maybe two variables. With two variables it's easy, but with I guess it will depend on 4 variables. And it was found just recently. It follows from the proof of the Goncharov Trimester conjecture for logarithm. I will explain later on what I mean by that. And for n greater or equal than 5, there are some examples, but they are very degenerate again, so they depend on maybe 2 variables or so. And this equation has already, I guess, about 500 terms. So,
931.
931 terms. So, and this one has 22 terms, I guess. So you see that this becomes a little bit untrackable, and the goal of this talk is to explain how to get, for instance, this equation without computations, and where these equations in general should come from. So for n greater or equal than 5, basically, in my opinion, there are no equations found, but there are some examples, but they are very degenerate. Okay. And there is another reason why polylogarithms are interesting, and the reason is that actually various of polylogarithms are very interesting examples of periods, which appear a lot in various parts of mathematics. And to illustrate it, I will just formulate Zagier conjecture about it. I will not formulate the exact form of it, I will formulate a weaker form, but not to introduce too much notation now. So basically, it's the second reason why I think polylogarithms are so important. So there is a conjecture. And I emphasize it's not the exact form, it's a weaker form, but just not to introduce too much notation. So F is some number field. And then the question is to compute the value of the Dedekind zeta function of the field, a special value in the integer number n, where n is exactly the same n as before. So, and the conjecture is that there is a way to present it as determinant, where values of the matrix of the determinant will be linear combinations of polylogarithms. So, more concretely, there is some constant part which is some power of pi. I will explain in a second what the numbers mean, times discriminant. Okay, and then there is the main important part, is the determinant of the matrix where coefficients are some linear combinations of polylogarithms. Okay, so the conjecture says that there exist numbers, elements y1 and so on, ydm, which are inside the free group generated by the elements of the field. So these are linear combinations of elements of the field. And sigma j are embeddings of f in C. And the conjecture said that up to rational multiple, the special value of zeta function is some discriminant power minus 1/2 times pi in some power times determinant, and all the elements of determinant are some sums of classical polylogarithm evaluated in these elements under all embeddings in C. And actually, the exact form of the conjecture predicts how, like, these numbers y1 and so on, ydm, these elements, they satisfy some additional restriction, which maybe later on will appear, and this makes them kind of not unique, but how to compute them. So this is the statement of the conjecture. It's okay that I can write it in this form. Okay, so okay, so this conjecture is known in some cases. In n equal to 1, it's basically due to Dirichlet, classical Dirichlet class number formula. I mean, okay, it's weaker, of course, but
your points y1,
sorry?
y1
What?
until y.
Up to dm, where dm is some number which is depending, which is the rank of the case theory. Actually, it is either the number of real embeddings or the sum of real and complex embeddings.
Number complex.
Sorry, complex embeddings or real sum of real and complex embeddings.
Except for n equal 1.
Okay, so
N equals 1.
yes, okay, sorry, except for n equal 1, where it is the sum minus 1.
The other rational is also 1 over 0.
Okay, so n equal to 2 was done by Zagier back in the 80s, and n equals 3 was solved by Goncharov in the middle of the 90s. The paper is 1994, I guess, but it was done before, I believe. And n equal 4 is our recent result, and it will appear soon. For all other cases, it is open, and it is not a coincidence that basically the understanding of polylogarithms of weight 4 and this conjecture in weight 4 it kind of goes up to the same weight. Okay, so let me now, after this introduction, let me talk about 5 conjectures. So let me start with giving a proof of 5-term relationship. So there is a very beautiful proof of this relation, which comes from the interpretation of this single-valued form of the logarithm as a volume in hyperbolic space. And this is well known, and I'm not going to talk about it, because it is something which is very hard to generalize to higher weights. Okay, so it's part 2, 5-term relation. Okay, So how to prove such functional equation? So the easiest way, of course, is to differentiate and to see that the derivative vanishes. So for that, we need to compute the derivative, and derivative here means, of course, the corresponding one form. So it can be computed, and here is the answer. So if you think of z and 1 minus z as another argument w, this is a very nice antisymmetric for minus logarithm absolute value of w, the argument of z, plus the same thing where z and w are exchanged. But here we specifically put w equal to 1 minus z. Okay. And I want to show that when we take the derivative, then the corresponding thing vanishes. Of course, it is easy to prove it directly, and I want to give somehow more, less computational proof. So to do it, let me introduce some notation, which I will use later. So for a second, we forget about this context, and I want just to talk a little bit about Milnor case theory. So let F be arbitrary field, be a field. So then one can define the following group, Kn Milnor of F is the following group. One takes the nth wedge of F cross. F cross is F without zero viewed as multiplicative group. And it's huge abelian group. If F is something like function field or a variety, for instance, it's just enormous abelian group. Then one takes a wedge nth power, which will be even huger. And then one factorizes over some elements, particularly over elements of the form x wedge 1 minus x, wedge something else, y 3, and so on, y n. So all these tensors, which have two components which sum to 1, they are killed. These elements are called Steinberg elements, especially when n equals to 2, I guess. Okay. So this object appears a lot in number theory. Sorry? No question?
It's not right for 2, right? For 2 torsion.
Yeah.
X tensor X isn't 0 in K2.
That's correct. That's a good point. Honestly, I want to work all the talk modular torsion here. I can either say that by F cross, I mean actually F cross tensor Q. Or just, okay, so everything is modular torsion. Thank you. Okay, so, okay, let's think about K2 for a second. So, of course, as this definition predicts, K2 is just the factor of H2 of F cross. And one can write down the resolution, which is very easy to do. This is a free group on elements of F, and the element x goes, this matrix delta, goes to 1 minus x wedge x. So one can ask the following question. Are there any relations in this group which are killed uniformly? The answer is yes, there is a relation. It's exactly the 5-term relationship which I wrote before. So maybe let me write it down as a lemma, that delta of A minus B plus B divided by A minus plus 2 other terms vanishes. So let me first prove that, and then I will explain why from this the functional equation follows.
So your ZF, does it include 0 and 1?
Sorry?
Your ZF, when you make this map, you should probably...
Yeah, they should be modular, yeah, they are killed. Let's think of them as
They
zeros.
are killed, it's
Okay, 7 to 0.
Yeah.
You're
Okay.
not sure.
So now the key computations comes in. So let me prove that this equals to 0. Of course, one can just open the brackets.
P0. doesn't blow up, it's quickly the observations.
Okay.
So because of that, it's okay.
So the key part.
Your analyst.
I want to prove this relation. So how to do it? Consider a sequence. Given by recursive formula, xn plus 2 equals 1 plus xn plus 1 divided by xn. So this sequence is 5 periodic. And this is a computation, which I'm skipping for now, and I will explain later on where it comes from. But basically, this fact that this sequence is 5 periodic is cluster algebra phenomenon. And from this, everything follows. Because when one computes sum delta of sum of elements xn, minus xn, it equals to sum 1 plus xn wedge xn. So the sum is from 1 to 5. And then one can use this recursive formula, which will be sum of xn minus 1 times xn plus 1 wedge xn. And then it is a telescopic sum. Xn minus 1 wedge xn minus xn wedge xn plus 1. I'm using this fact that I have the wedge 2 of cross, so multiplicativity and antisymmetry are coming in here. And this vanishes because it is 5 periodic and this is telescopic sum. So this is a key computation. Okay, how from this the proof of the fact that the derivative of this relation equal to 0 follows? So this is obvious because actually the form minus logarithm absolute value of w d argument of z plus logarithm absolute value of d argument of w has exactly this property. It's antisymmetric in z and w and linear when z or w is presented as a product. And so it basically is a function from k2 to omega 1. I mean, this is a formal computation, so all the properties class of this function and so on is not important. And of course, since we plug in 1 minus z and z, it's exactly the image of the delta, sum of delta. This form applied to sum of delta equal to 0. Okay, so this is the proof of the 5-term relation. Let me just mention while I'm preparing the report that this 5-term relation is very crucial because it is known that basically all functional equations for the logarithm follow from it. There are some restrictions, so this is a result of Suslin, and I think the correct form is that if you have a function field of a variety which is rationally connected, then if there is some relation for the logarithm on this functional equation on this variety, then it will follow from the 5-term relation.
Suslin, I thought that's Wojtkowiak.
Sorry?
Isn't that Wojtkowiak, not Suslin? Zagier. Well, you can ask them.
So I thought, so it is basically the homotopy invariance of the kernel from P2 to wedge 2f cross, which I thought will follow from the identification of the kernel modular torsion with the K-theory. But I...
No, there's an elementary proof of Wojtkowiak, just in terms of rational functions.
For algebraically closed field.
For one variable.
One variable over algebraically closed field. And I'm saying more general situation, when you have not algebraically closed field. I mean, if you have many variables, then it's not enough to use this result of algebraically closed field, I guess. Okay, so the next topic. The logarithm and cluster algebras. Okay, So the previous statement about functional equations for the logarithms was said to kind of explain that this is not a very serious thing. So I will now produce a lot of functional equations for the logarithm, but they all follow from 5-term relation. So don't take it too seriously. Okay, so let me first talk a little bit about cluster algebras. So I will be very concrete, and I will explain the main idea behind cluster algebra phenomena. I'm not going to define cluster algebras, and cluster algebras are not in algebras actually, so it's not very important. So here is a very elementary idea. So consider a quiver. A quiver just oriented graph with a bunch of vertices, no loops, and no two edges going in the opposite directions. Something like this. And consider variables x1, x2, and so on, xr attached to these vertices. So then one can do the following thing. So this configuration, a quiver and a bunch of functions in the vertices, is called a seed in cluster algebra business. And if you have a seed, one can do mutation. Mutation is a procedure which changes the graph and changes the variables. And let me say now that I will explain the combinatorial part, and then I will explain more, maybe easy to understand symplectic geometry and interpretation. But first I want to do the elementary combinatorial story. So consider a quiver Q with functions x1 and so on, xr in the vertices. So what is a mutation? So mutation is a procedure where you choose a vertex, one of them, like for instance this one, mutation. You choose a vertex. I will call it mu3 because the vertex has number 3 here. And then I redraw a graph according to some combinatorial rules and redraw the functions. So firstly, how do I redraw the graph? So first I take all the edges which come in and out and exchange their direction. Then if I had two edges which come in and out, I add their composition.
I think you don't touch
No.
the other.
Only the mutation, the vertex where you do the mutation, you change the direction.
I think that's correct.
It's not what you did in your
No,
previous one.
the top thing.
Oh, sorry, yes. And then I kill the double edges. So there are basically three rules. So first, so this is mutation in the vertex K. So exchange direction of edges going in or out of K. The second thing is add compositions. I mean compositions, of course, in quotation marks. For every pair of coming and outcoming edge, add one more. And the third one is kill all these situations. For every two, if you have two edges like that, one can kill both of them. And this exchanges the graph. And also one needs to exchange the variables. And how one exchanges variables, one don't touches all the variables other than xk, xk. So x1, x2, and x4 will be fixed here. And x3 is substituted with another function. And this function is given in general by the formula, so mu k star of xk is the following thing. So it's a Laurent polynomial where in the denominator one has xk, and in the denominator one has a product of all x's which are incoming there, plus product of all x's which are outcoming. In our case, I take, instead of x3, I get a fraction where x3 is in denominator, and here I have x2 plus x4, one incoming, one outcoming variable. So this is what is called a cluster mutation.
Your
And-
mutation doesn't have to be quiver any longer apparently?
Sorry?
Your mutation doesn't have to be quiver?
No, it gives a quiver with new rational functions on it.
I think you said something about no loops.
Sorry?
You now seem to have to be
Maybe loops, but not short loops.
Okay, and then what is the cluster algebra story? The cluster algebra story is as follows. So one does that, mutate, and looks at all the functions which come out of this. And surprisingly, this procedure gives some interesting results. So first, let's consider an example, and then I will say the general statement. So first example, the main example is the example we discussed before. So one take a quiver, which is just one directed edge, with the functions, let me call them A and B here. So then, what one can do? So this is a quiver. One can mutate it in B, or one can mutate it in A. Let's mutate in B. So in this case, we need to exchange the edge, and instead of B, we write A plus 1. 1 substitutes the absence of outcoming edges. 1 plus A divided by B. And here one can also mutate in A and get 1 plus B divided by A and A. The next mutation will give 1 plus B divided by A and 1 plus A plus B divided by AB. And here the miracle comes in. So when we mutate again here in this vertex, 1 plus A plus B, 1 plus B over A. Oh, sorry, here's the Okay, and here's the miracle comes in. So when one mutates here again, one gets 1 plus A plus B divided by AB. And this all is divided by 1 plus B over A, which should be something very complicated, but actually the denominator factors out. And this is 1 plus A over B. So one can observe here several properties of cluster algebras which are true in general. So firstly, here our procedure is 5 periodic. And there are no other mutations because if you do the same mutation on the same variable twice, you will get back. So this thing is 5 periodic. Also, every time we get Laurent polynomials in A and B with positive coefficients. So periodicity is not true in general, but this Laurent phenomena and positivity are true in general. And this is one of the main cluster algebra statements. And if you will look at it, one can see that actually if one denotes this variables x1, x2, and so on, then we will get exactly this sequence, which is 5 periodic. And here one can see it.
I'm confused with the directions of the arrows. So you didn't switch it?
Yeah, so they are switched every time, except that...
You just drew it the other
Oh, right.
way.
Oh, I see.
Yeah, so
The
it's kind of...
is not part of this structure.
Yeah, same. Okay. So let me formulate this speed. 3 properties.
Excuse me.
Yep.
Is this coincidence, happening coincidence, or is there any reason why is it complex?
You mean?
It is coincidence by chance, or is there any reason?
I will now formulate the general result. So the fact is that it is not a coincidence, it's a part of general theory, but the whole theory was quite surprising, I guess, when it was developed in the beginning, because a lot of elementary recurrences with periodicity properties which were considered coincidences were explained in this bigger theory. So, but again, so far it is all without any explanations, it's pure combinatorics.
Was this known for in the cluster community?
You mean?
This kind of 5 periodicity?
Yes, it is basically the first example of cluster algebra. So it's the first example. Yes. Okay, so let me formulate facts maybe about cluster algebras. And first two are not relevant first at all. So the first fact is that all variables. By variables, I mean everything which can appear by this procedure, starting with any quiver, are Laurent polynomial in initial variables with positive coefficients. So this Laurent polynomial fact is not super hard, and there are now two proofs by Faminza-Levinsky, more combinatorial, and by Kontsevich, Hawking, Keel, and Ross, more conceptual. And the positivity is very hard, and also there are now, I guess, two proofs, but both of them are very hard. And this part is not very relevant to the cluster algebra business so far, which I need. Okay, and there is another fact which says that the number of seeds one can get is finite. So seed is a pair of a graph and functions. And finite means that you have some periodicity phenomena and only finite number of graphs with functions appear. If and only if the initial graph is a Dynkin diagram. So basically, the so-called cluster algebras of finite type, they match the Dynkin diagram classification. There is some issue about simply laced, non-simply laced, but I'm not going into that. Particularly, this is of course A2 example. And also notice that if you have a big graph, one can do mutations, and one can do mutations only in one subgraph of this graph, and then the same periodicity phenomena will hold. It's not obvious at all. It's true. Okay. Let me now explain the main idea, how it's related first to Polylogarithm, then to higher Polylogarithms. So, actually, and this is maybe the main observation of Hausdorff and Goncharov, in the correct, from the correct perspective, the logarithm in its quantum version explains the cluster algebra business. There is a, I'm not going to talk about it, but there is a non-commutative version of cluster algebra mutations where you substitute these variables with non-commuting variables with quantum torus coordinates, and then the corresponding quantum version of mutation will be conjugation by the quantum logarithm power series. But the phenomena which I will talk about it is the semi-classical limit of it. So the idea is as follows. So consider this quiver once again. So let alpha ij be the number of arrows from I to j minus the number of arrows from j to 1. So basically the quiver is of course nothing but this antisymmetric matrix which is this alpha ij. It is just a pictorial representation of this matrix. So one can think about, so a seed I, let me call it gives rise to a thing which I would call K2 torus. So K2 torus is a torus, split algebraic torus, with characters x1 and so on xn, and equipped with differential form, which is kind of two form, like almost symplectic form, closed two form. And this two form is not arbitrary two form, is a two form coming from K2. Cognitive ecology. So to be more precise, so to this, so there are variables in total. So to this thing one associates the torus gm power r, let me call it t, and a form omega. So I can write a couple of versions of it. So the main one will be some alpha ij xi wedge xj, which lies inside the function field wedge 2 of the function field of the torus. But it also gives rise, of course, if one looks at the corresponding element in Milnor K2 to the corresponding K2, kind of K2 form. And from K2 there is so-called differential symbol, which sends element A which B to dA over A which dB over B in the Keller differentials. And so there is also a version of this omega, which is the usual differential form, and this is classical invariant form of on the torus. Sum alpha ij dxi over xi which dxj over xj. Okay, so one can think about this cluster algebra data, this seed, as just a torus equipped with such a form, nothing else. But one should think of it not as just differential form, but as maybe an element in the wedge square of the function field. And then there is a main statement, which is completely obvious. I mean, it is a simple computation. So, lemma is that so if one does consider the form omega in the mutated, for the mutated quiver, and the form omega for initial quiver. And the statement is that they are the same in K2. The corresponding classes of form is the same in K2. Which means that their difference should be sum of Steinberg elements. And actually it's a unique Steinberg element, which is nothing but kind of the delta, so the basically the logarithm of a thing which is the minus product of xi over all incoming edges divided by product over all outcoming edges of xi. This is called so-called cluster X coordinate. So this is the main idea, particularly in the case of the 5-gon which we considered before. Oops, sorry. So the form which we consider here is A wedge B. The form we consider here is 1 plus B divided by A wedge B. And the difference between these two forms, with the minus sign because the edge is reversed. And the difference between these two forms is exactly 1 plus B wedge B, which is the logarithm of minus. And of course, when we take the co-product of sum of the logarithms which are written on the edges, the sum will be equal to 0 just because it is kind of the cyclic sum. Okay. So now let me okay, I don't have too much time, so I will skip the big story about motivic approach to polylogarithms and mixed-state motives because it's kind of classical. I guess a lot of people have seen it in different forms, and of course it is well written. So let me continue with this maybe ideas. So
can I ask, were these things found by Goncharov and you?
So the de-logarithm situation was introduced by Fock and Goncharov. And the new thing is the one which I'm going to talk now about how to generalize it to higher polylogarithms and get functional equations for higher polylogarithms from that. So the idea is that if one starts with the cluster algebra with the Dynkin quiver, which has this periodicity phenomenon, the corresponding graph of all quivers will be a special, some generalization of a special polytope. If the quiver is literally a n-type, then it will be such a polytope. So let me, for instance, consider this situation. So basically, I consider the quiver like that, and then I will have I tried to draw in the beginning of the lecture the such a polytope completely failed, but something like this. So each vertex of this polytope will be one of the cluster tori. So each of them will be one of this cluster tori with this two form. And the difference between two forms, so if you have some form omega 1, omega 2 here, then the difference will be the co-product of the corresponding de-logarithm, element in B2 if you wish. And every closed path in the edges of this polytope will give a functional equation for de-logarithm. But the situation here is so that it actually will be a sum of the passes going through 5 gons and 4 gons, and one of them is 5-term relation, another is trivial relation, so it's not interesting. But here is the main idea. So main idea how to go beyond. How to go beyond the d-logarithm situation is as follows. So key idea. Consider omega power k form. Or one can simultaneously take everything and take exponent of omega. And consider how this form changes when one moves along this polytope.
What is omega?
So omega is this. So we have a torus with a form omega, equipped with a form omega. This is K2 form which I wrote down before. And one can look at its square, for instance, or cube or something. And this will be also invariant in Milnor case theory, of course, because it is a square or power of a form which is invariant in Milnor case theory. So what will happen is that on every edge, so on every edge one can get a Steinberg element, but now not literally Steinberg element, but the corresponding element in B2 tensors the edge power of the F field cross. So the key idea is that one can consider the, okay, so let me now be a little bit faster here. So one can consider the Lie algebra of mixed state motives, which is a little bit conjectural, but one can think of it as mixed for structures with geometric origin, and then it's fine. And one can consider the Chevalier-Lindbergh complex of this algebra. And let's, for instance, look at the degree 4 part. So polylogarithms give motivic version of polylogarithms, give examples of elements here. And this is how it looks like. So the main property of this Chevalier-Lindbergh, it is example in grade 4. The main property of the Chevalier-Lindbergh complex of the motivic Lie algebra is that it is basically acyclic. The only, so the cohomology of this complex should be equal to motivic cohomology of a field with rational coefficients. And so when one works with irrational varieties like this cluster algebra function field, basically the only cohomology it will have will be the Milnor case theory in the top degree. And so what one can do, one can so every vertex of our polytope give us an element here. Every edge allows us to integrate the difference between two elements here. Every 5 bond allows us to integrate it once again. And every 3-dimensional polytope allows us to get actually a weight 4 polylogarithmic function. And if everything lives in a bigger cluster algebra, where the bigger polytope is like such a 4 polytope, for instance, one gets a functional equation for weight 4 polylogarithms in this way. So this is the key idea.
But these polytopes are always associated?
They're generalized associated with this. But the algebra can be not just what I wrote, but it can be, there can be so-called frozen variables, the variables where we don't mutate. And so one can get a bigger variety.
How do you know the element in the kernel comes from a classical polylog, not a multiple polylog?
Yes, this is
It's equivalent to...
of course, important point. So the answer is that it will come from multiple polylog. This is why I wrote here L4, not B4. So, so in this way, one can get a functional equation for multiple polylogarithms, but it will be very explicit. And the polylogarithm one has here has this very simple coproduct, which has a combinatorics of Stashev polytope. And let me just finish with the fact that the key motivation behind this work, at least from my perspective maybe, was to explain the results of Herbert-Gungel, the functional equations I've explained before. And this result is basically the statement that if one looks at the multiple polylogarithms of weight 4, one can compute coproduct in B2 wedge B2 part. And the claim is that the kernel of this map is exactly the classical polylogarithms. And if this, so to show it, one need to show some complicated way to rewrite some of multiple polylogarithms with coproducts which are give 5-term relationship using classical polylogarithms. And this was the thing which was solved by computer-assisted method by Herbert, and it is very complicated formula. So one can get it from this story in the following way. So one takes the formula which comes out of this procedure, which is very explicit and simple. I can write it down, but it will take one line.
For which class? For which?
For A4 cluster algebra. Actually, it will be configurations of 7 points on P1. And then by a very simple procedure, some sort of anti-symmetrizing, changing variables, and so on, one gets the Gangles formula from that.
And somebody had the temerity to actually look at 931 terms?
Sorry?
Somebody actually looked at 931 terms and so they agreed?
In a sense, this also explains where the formula comes from, but I mean, I can... No, so to do it, you don't need to come to all this business with writing down these relations. They kind of follow. Yes?
And what's K? You have considered
Omega to the K? You mean this omega? Yeah, it is just the form wedge, K.
Like maximum?
No, just sum, any. In this case, okay, so let me write. In this case, we do wedge 2, omega, wedge, omega. And look at it. Yeah, so I think all the details will appear in the joint paper with Alexander Goncharov, which will appear very soon, like in a couple of days. Okay, yeah, I think that. I'm sorry for this.
So, questions?
If you take the moduli space of 7 points on a Riemann surface and you're a 7, and you look at iterated integrals on that, so you can express that algebraically using kind of bar construction. You look at the weight 4 part, so iterated integrals of length 4 in certain cross ratios, then you automatically get an action of the group sigma 7 on that, and you can decompose it into, according to the representation theory of sigma 7, and you immediately pop out functional equations in multiple polylogs in weight 4 in 4 variables. Is that the same one as the one you've written up on? Is that the same functional equation as the one you've written down?
So firstly, this is a question I would like to ask you, but honestly, I don't think so. So the key thing, the key non-trivial thing is that the function one gets from the Stashev 3 polytope is very simple, and it can be written down using just these 3.
So did you
1,
3 or 4? Because before you said A4, and now is it a 4-dimensional polytope or 3-dimensional?
So 3-dimensional polytope produces element here. 4-dimensional polytope produces functional equation. And the fact is that the corresponding function will be sum of the des2 polylogarithms.
Yeah.
Very explicit one. And having a very explicit functional equation for weight des2 polylogarithms, one can play a little bit with it and get this effect. And if you will start this functional equation with polylogarithm of des4, for instance, it is very hard to imagine for me how to get it. I mean, it's a hard problem. So the problem is that the co-product of a weight 4 polylogarithm has very complicated combinatorics. It's very hard to come up with functional equations for it. And here, the functional equations come from this Stashev polytope.
But does the symmetry group of order 7 play a role? Because this Stashev polytope admits an automorphism of action by the symmetric group on n letters, and that should simplify using the representation theory of the symmetric group. That should simplify the combinatorics considerably.
So here is the answer. So the cluster algebra structure, which one can put on M07, actually depends on the cyclic choice of the vertices, of the points. So if one fixes a cyclic ordering, then everything will be diagonal invariant. But if one tries to apply general symmetric permutations, this structure is killed, and all these functional equations and so on are killed. But it is exactly what you need to do to get the Herbert-Gangles formula. One needs to start to apply them and somehow.
Any other questions?
There is a feeling that you are computing maybe homology of some sheaf on the cluster variety, because you are basically writing down the check complex for the
cluster varieties.
Yes, yes. Basically, this is sort of a hypercohomology. So the statement is that one can associate to cluster varieties some sort of the higher Chern class, but it's not clear what this Chern class is and so on. So it's a bit mysterious to me. But the main key thing is that one can do everything explicitly using combinatorics of cluster algebras, not only prove that something is like integrable.
Can you, I'm sorry, was there I have a question. Yeah, can you express things in terms of motivic cohomology, in terms of a comodule under the motivic fundamental group? I mean, so I always think of things in terms of cycles on affine spaces or on cubes. So for example, the K2, I mean, you would have 2 points and then a one-dimensional cycle whose boundary was x wedge 1 minus x or whatever.
So my general feeling, which I got from Goncharov at least, who had experience to thinking about this problem, is that to write down something using multiple polylogarithms or integrals, so multiple polylogarithms immediately give you algebraic cycle, but if you write it down as an integral, it just gives an idea of what the algebraic cycle is. It should be not super simple to get it.
I see.
But we can talk about it next
Yeah.
time.
So no other questions? Oh, there is one. Yeah.
In the process towards the 131 class, there was the 122 class, where you can express I3, 1, and 2 variables as some of. Do you have a geometric interpretation of those 122?
Yeah, exactly. So, but it is not. So this 122 equation which you are talking about is exactly the statement that this conjecture. So this sequence is exact, and exactly this is necessary. One is the ingredients in the Zagier conjecture's proof. And to get this 122 term equation, one needs to take this simple functional equation which is obtained by this construction, and then basically sum it with some permuted in some sense, generally a little bit, and so on. Yes. It's not completely a geometric interpretation of your equation, but your equation comes from the geometric equation by some simple procedure. This is the key.
Are there any other questions that I can't see? Yeah, there's one that I can't see.
In the proof of Zagier's conjecture in weight 3, I remember that there was a map from the homology of the general linear group to the plot complex of weight 3. In this case, do you also get a map from the homology of general linear group to weight 4 plot complex?
So the proof of the Zagier conjecture in weight 4 splits in 2 parts. One part is what you are talking about, basically, and this constructs a map, the corresponding presentation of the corresponding period as linear combination of multiple polylogarithms. And this part is absolutely something I was not talking about. It is also non-trivial, but it is more close to the proof in weight 3 case. And additional problem in weight 4 is to rewrite it using the classical polylogarithms, and this is the statement. So it is needed, but it's not the topic of this document.
Anyone else? Okay, we thank the speaker again.